Yesterday we saw the Master Theorem, and let me recall what it says. It says if you want to check that the word W satisfies a formula phi, what do? You guess the set of FUM subformulas that are going to hold infinitely often. You guess the set of GWR subformulas that are going to hold almost everywhere. And you guess the stabilization point. Then you check that your guess for X is correct, assuming that your check for Y is correct. You check that your guess for Y is correct, assuming that your check for X is correct. And you check that the suffix WI satisfies the formula it should satisfy, the formula phi after prefix W0I, assuming that your check for X is correct. Okay? That's what it says. So now let's see how to derive, how to use this theorem to construct automata for LTL, right? Good. The first thing we can do is a very little thing, which is let's move, these two, they do not depend on I. So let's move this I here. Okay? So then we have condition 1 becomes there exists an I such that blah, blah. Okay? Well, and remember, this is going to help us, this theorem is going to help us because each of these checks, is a check where this formula here is an FUM formula. So actually, this is a check of the form W satisfies GF FUM. And we know how to do that. We did it explicitly, right? It was very simple. The same happens here with this. Here, remember, we need to use Rabin automata if we want deterministic automata, for example, because the formulas of the form FG something in GWR, there may be no deterministic Bichet automaton. And then we have this one, which is, the nice thing is that this is a GWR formula, but we will see a little bit about how to do this because, this is a formula that is changing as I changes, right? We are changing, we are tracking, which is the formula that remains to be checked, and therefore this is a moving target, and we'll see how to do this in a moment. Okay, so the first idea is very simple. Let's introduce this language, L, for an X, a Y, and a J of phi, where J is 1, 2, 3, and this is going to be the languages of the words that satisfy that for a certain choice of X and Y satisfy the property J. Okay, so you fix an X and Y, and then you see which word satisfy 1, which word satisfy 2, which word satisfy 3. And then immediately what you have is that the formula, the language of the formula is a Boolean combination. Okay, you take the union over all possible guesses for X and Y. It's a big union. It's a union of you can have exponentially many sets here. And for each, once you have fixed X and Y, what you have is an intersection of languages, right? The important thing is that whenever you have a class of automata which are closed under union and intersection, this immediately tells you that all you have to do is give automata for these three, okay? Because then you are done. Good. So the idea is then construct automata A, X, Y, J, recognizing L, X, Y, J, right? And then take the closure under union and intersection. Well, let me just review in case you don't remember this or you have never seen it maybe, how to do union and intersection of the classes of automata we are going to be interested in, which are non-deterministic Bichet automata, deterministic Bichet automata, non-deterministic and deterministic Rabin automata if you want, although we are actually interested in the deterministic ones. So actually, let me just do it a little bit more general because I think it's actually cleaner. Let's take a generalized Bichet condition that, remember, is a positive Boolean combination of sets that must be visited infinitely often. So you say, I want to visit this set infinitely often, and I want to visit this set infinitely often, or that set infinitely often, and whatever, right? So you have a positive Boolean combination. So if you take two DBAs over the same set of atomic propositions, as usual, set of states, transition function, initial state, accepting condition, then how do you do the union? Okay, these are deterministic Bichet automata, right? So how do you do the union? Well, the states are going to be the product of the sets of states. The initial state is the pair of initial states. The transitions are the usual, right? You take the pair, you pair the transitions. And what is the only interesting thing is the accepting condition, which using a little bit of semi-formal notation. I hate when you do this completely formally because it hides completely the meaning. We're going to call it alpha 1 cross product with Q2 or Q1 cross product with alpha 2. Okay, and what is this cross product operation? Well, let me just explain it with an example. Assume that alpha 1 would be something like visit this set of states infinitely often, or visit this set infinitely often and this set infinitely often, right? And assume that alpha 2 would be something like visit this set infinitely often and visit this set infinitely often. Okay, so what is then this operation, this thing alpha 1 cross product with Q2? Well, you take this and you replace every set by its set cross product with Q2. Okay, so this is the operation. And then you do the same thing on the other side and you take the OR. Okay, and now you have again a positive Boolean combination telling you that you have to visit some sets of the product product automaton infinitely often. Okay, so you had again a generalized Bucci condition. And why is this working? Well, essentially what this is telling you is that if you have a run which satisfies this condition, the run will satisfy either this or that. If it satisfies this, this means that the projection of the run onto the first component is going to satisfy this condition, and otherwise the projection on the run on the second component is going to satisfy the same condition, okay, or the condition for the second automata. Okay, everybody happy with this? Good. So how do you do intersection?
If you think of it as an LTL formula, in terms of positive Boolean combination of GF, then it's just a disjunction.
Yeah, it's just a disjunction. But I wanted to do it a bit more explicitly in case that you haven't seen this before. And
do you assume that the transition relation is complete? Because you have the transition, you assume that
well,
the component
these are DVAs, so yeah.
also complete.
Well, in a DVA, you all typically assume that the transition relation, that you have exactly one transition for each letter.
But it's not that you don't have the transition relation for some of
No, I mean, assume it is complete. Yeah, okay. Assume it is complete. And then for the intersection, it's exactly the same thing, but with an and here. Okay? Well, anyway, good. So you have the intersection there. Okay, and then which is the thing to remember, keep in mind, is that the size of both the union and the intersection is the product of the sizes of the components, right? And now if you are doing it for n BAs, we have an n here now, right? We have two n BAs, A1 and A2. Well, the idea is that now you don't have the same complexity for union and intersection. Union is cheaper than intersection because for union you just put the n BAs side by side, right? And that gives you a new n BA. I am assuming that, oh, actually I forgot to change that, that you can have now more than one initial state, and then it's really putting them side by side. You take the union of the states, the union of the initial states, union of the transition relation, the fitting condition is just the disjunction, okay? And the intersection is just exactly as for DVAs. So now we have that the size of the union is the sum of the sizes, not the product, and the size of the intersection is the product of the sizes, okay? And then in both cases for DVAs and NBAs, some algorithms are going to assume that the accepting condition, this positive Boolean combination, is in disjunctive normal form. Okay, so if that's the case, then once you have obtained your final result, you will have to put the accepting condition in disjunctive normal form. That may involve an exponential blow up in the size of the accepting condition. Okay, good. So what about D arrays and N arrays? Well, it's just exactly the same. Instead of, but you know, the atomic propositions we have, if you want, is not visit this set G infinitely often, but visit G infinitely often and visit F finitely often, but otherwise it's just exactly the same. Okay? It's just you change the atomic proposition, but otherwise nothing changes. And therefore, in particular, you are going to have exactly the same results about the sizes of the automata. Yeah. This is the generalized rubbing condition, so to speak. And again, you are going to have the result that sometimes you have to put that in disjunctive normal form and so on. Yeah. I'm using the generalized, actually, yeah. We should call it deterministic generalized rubbing automata or so on. You call them rubbing automata actually when you have this disjunctive normal form essentially. Good. So now how do we construct? Let's start with DRAs, right? So if you, the algorithms that you may know or not know is that if you have an LTL formula, how do you construct a deterministic Rabin automaton for the formula? Well, you construct a non-deterministic Bucci automaton, and then you translate that non-deterministic Bucci automaton into a deterministic Rabin automaton using Safra's construction. Okay, and the result is going to be at most double exponential. You have at most a double exponential blow up in the size of the formula. Well, let's take an alternative route here, which is, well, we are going to construct a DRA, a phi for phi, right? Assume that phi has length n. Then we are going to take the union of DRAs a xy, one for each pair xy, right? And how many pairs can we have? Well, exponentially many in the size of the formula, right? So the size of the automaton a phi is going, I'm being a little bit sloppy here with the notation. The size of a phi is going to be at most, you know, remember that the size, the size of the union of two deterministic Rabin automata is the product of the sizes, right? So what you have is the size of this automaton to the power 2 to the O of n. Okay, looks very dreadful. It is dreadful, but you know it's just as dreadful as the Safra construction. How do you construct the AXY? Well, it's going to be the intersection of three deterministic Rabin automata for these three conditions: 1, 2, and 3. The 1 for 1. Let me just delay this to the next slide. It's going. This is the one that needs a little explanation. You know, the 1 for 2. This is just, you know, we know how to do this because each of these formulas, it is just the form GF and then FUM formula. And you are going to have a double exponential size, which cannot, and in general, it cannot be smaller. And
FG, what is the subscript FG though?
You know, is this psi with advice y.
What's the subscript FG?
The subscript FG, remember, the idea is that the x are assumed to hold infinitely often, and the y's are assumed to hold almost everywhere. Okay, and therefore, when you apply the advice, you get different results because you have different assumptions. Okay, so this is what you get, right? Believe me for the moment that this also has size at most double exponential, right? And then what you get is this. This is the size, then the maximal size of one of these components is this. And to this power, and this is the magic of exponentials, right? This is not triple exponential. This is still double exponential. Okay, everybody happy with this? Good. So let me tell you how to do this, the AXY1, right? And maybe let's try to do it with a drawing first. Okay, so. The question is that you have to remember what we have to do, right? Well, I'll write it when I get to the slide. So we have to check whether there exists an I greater than or equal to 0 such that WI satisfies phi after 0i with advice x GF. Okay? Good, so then we are going to do this with an automaton whose states are going to have two components, right? And the idea is the initial state is going to be just phi and, you know, phi with advice GF, right? And we are going to use the first component just to remember which is the current formula, this current formula, right? Because otherwise, while we are trying to check this, we may lose track while we are reading the word, we may lose track of what is this. This is changing all the time, right? And then we have to keep track, we have to remember it. And for that, we use this first component, right? And for the second component, remember that now this is a formula that we know how to check, right? Because we are applying the advice, so this is actually a formula of GWR, right? And for the formulas of GWR, we have an automaton, and the automaton has a special state which is false, and we know that the formula fails if we ever visit the state false, right? And if we never visit the state false, the formula holds. So what do? We then construct the transition relation accordingly. So for instance, here, if we now read the letter nu, then the first component becomes phi after nu, okay, and the second component becomes whatever it has to be in order to check whether this formula holds. And now what happens if we ever reach a state of the formula psi false? Well, then we know that our attempt at checking this, you know, we were guessing, oh, let's assume that I is greater than or equal to 0, right? Okay, that guess failed, right? So then we just say, okay, well, then we just continue, you know, assume this is a sort of epsilon transition, we just continue with psi x gf, because now this is where we are now, right? This is what has happened after in the meantime on the left hand side, and then this is our next try. And remember that what we are guessing here, this is actually the stabilization point, and it doesn't matter whether we hit exactly the stabilization point or anywhere behind the stabilization point. So therefore it doesn't matter, you know, we have lost some opportunities maybe for checking, the I could be in the middle, the stabilization point could be in the middle, could be while we were checking this, but it doesn't matter, because now we continue with another I, which is also valid, right? And this continues like this. So and if we hit false again, then again we continue and so on. Okay? So as you can see then, the number of states is going to be the number of states that you can generate from phi, which is double exponential, times the number of states which you can generate from here. It's again double exponential. This double exponential shows up everywhere whenever you want to do something. But that's it. I mean, you don't need to apply any complicated thing. Yeah.
You need just the Rabin condition to make sure you don't hit the false infinitely often.
Exactly. Yeah. You just need the Rabin condition to show that you don't hit the false infinitely often, and that's it. Okay. Good. So actually, in fact, you are going to have only one single. No. You don't have. Well, you have one Rabin pair. Yes. I think in this case you only have one Rabin pair. No? Even coefficient, yeah. You don't need actually Rabin, it's just coefficient. Okay, so then this is just saying what I just told you, that the DRI for the word satisfying this condition, the states are pairs of formulas, this is the initial state, the first component tracks, you keep always computing this, so that you can use it if you need it, and the second component just simulates the automaton for this. And then if you reach a state psi false, then you move to that state. Okay, and the accepting condition is very simple. Okay, so that's the first translation. Now, and that's the most important one for us, because you know the problem of constructing deterministic Rabin automata. This is a problem that has been devoted a lot of attention in the literature, and at least what everybody I think will agree is that this is a completely different approach. It is really different from anything that was tried so far. The main difference being that all the other algorithms, they give you a monolithic construction. So they tell you, okay, here is the automaton. And here we are giving you a structured construction. We are telling you, construct this army of little automata, right? And you get the final result by composing those little automata. That's the main difference.
No, but I think McNaughton proved exactly in this way. He translated automata to expressions, and then for every expression construct automata.
Okay, maybe I am rediscovering McNaughton's. I don't know.
Why not?
Well, because really the key thing here is not starting from an omega automaton, but starting from LTL form.
Yeah, this is also something.
That's really taking advantage of significant.
this is also which is something which is
Say,
important, yeah.
The difference
Yeah.
before was an attempt to modularize the construction. So they
Yeah.
went in two steps. One, to an omega automaton, to just to an NBA, and then determinize. And so now, that was actually the difficult construction. It took many years. That's what Metonton was trying to do. The idea here is, let's go back to the LTL formula, and instead of doing it in two steps, doing it in one step.
Yeah, so the idea here, if you want, is the approaches that were used so far were handling logic a bit stepmotherly, in the sense that you go from the formula to the automaton, and then you forget the formula. You only work with the automaton. Of course, this has a lot of value in the sense that automata are more expressive than LTL. Non-deterministic Bücher automata are more expressive than LTL, and therefore you are getting a more general result, right? But on the other hand, you are missing this opportunity of doing it in this structured way, which we claim has advantages. And LTL, you know, is important enough in order to be able to do it.
On the other hand, if I want to tell you, okay, please add past temporal connectives, now we have to rethink it.
We'll have to rethink things, yeah. Okay, what about NBAs? So if you want an NBA, well, again, you have to take the union of the NBAs, once for each x and y. But now remember, when your automata are non-deterministic, the size of the automaton for union is the sum of the sizes, right? So the size of A phi is going to be 2 to the n times the maximal size, actually I should write here, of one of these AXYs, right? These AXYs, they are going to be the intersection of three automata. But see, now here you have non-determinism, so in order to check condition 1, you can just guess the I. Okay, you guess the I, and then you move directly to the formula that you have to check, and you check it, right? So, and actually you can, it's very easy to construct an automaton for that of exponential size. And you know, the same for these things with, actually there is a mistake here, yeah. No, that's fine, no, it's fine, because, well, you know, this is one of those little tricks that you do in order to get an O of 2 to the n instead of a 2 to the O of n, but don't pay too much attention to that. It's not really very important, only if you are very interested in those things. And well, in the end, you get something like this. So in principle, we get a 2 to the O of n. Can we put the O there? I must say it's not something that we have worked out completely. Probably you can, but I don't think it's a very important point, essentially. I mean, it's, of course, theoreticians discuss those little points. You know, I had a colleague in robotics, give me 1 second, because a colleague in robotics once was asking me something. I was telling him, you know, but that's a double exponential construction. And he was saying, oh, you theoreticians, exponential, double exponential, why do you worry about those details? Anyway, so.
Maybe I missed it, but when I guess I, is there a finite bound on I, or can it be any?
No, but the idea is that you stay in a state, you have a non-deterministic automaton, right? So what you do is you stay in one state until you say, okay, now I do it, right? Essentially, that's what happens. Anyway, let me tell you about, so the idea is essentially, you know, Bernd, for instance, will have some use for the arrays. Well, I don't know if Bernd, but at least definitely Crystal, sorry, because they are very much used in, they are needed for probabilistic model checking. And of course, there is obvious use for model checking of MBAs. And let me tell you about something, I don't know if you know, limit deterministic Bücher automata. So the idea is that, you know, these, the arrays, they are really pretty expensive, and this is a recent attempt at constructing automata which in practice actually behave better. Okay, and the reason is that you replace the rubbing condition by the Bücher condition, which has some advantages when doing the model checking, when applying the model checking algorithms. So what is a limit deterministic Bücher automaton? So the idea is that a run is only allowed one single guess, or you could say, well, the idea is that, no, let me maybe, that a run is only allowed one single guess. Or if you want, it can be allowed multiple guesses, but they stay here in this initial component, and then at some point you jump to the accepting component. All final states of the Bücher automaton are here, right? And here, this part is deterministic. Okay? So here you may have non-determinism if you want, although our construction will give you also, at least if you want, an initial component which is also deterministic, and this is deterministic, and well, if you take this as deterministic, then in each run you are going to have exactly one guess, right? You stay here, everything is deterministic, and then at some point you decide to jump, and that's it. Then everything continues to be deterministic. Why is that interesting for, this is interesting for probabilistic model checking, and let me give you the intuition of why that's the case. So the idea is that if you take, imagine that you have an automaton where you can have, imagine that you have a non-deterministic automaton where you have two possible transitions with an A, and imagine now that there is a probability distribution on that A, on those A's. So you can take this A with probability 1/3 and this A with probability 2/3, right? So whenever you have a choice between two A's, you have you have attached probabilities. Well, then what happens is that in a Bushy automaton, a word is infinite, so you may go through infinitely many of these choices, okay? And then what can happen is that if you now think, imagine that the word A omega is accepted, right? The automaton, there is an accepting run for A omega. What may happen is that the accepting runs for A omega have probability 0, okay? Because each of them goes through infinitely many choices like this, and then in the end, each accepting run has probability 0. So the problem is, if you want to know now whether A omega is accepted with probability bigger than 0, you cannot reduce that to a problem without probabilities, right? Your automaton may accept A omega, but that doesn't, the simple fact that forgetting probabilities, your automaton accepts A omega, doesn't tell you whether A omega is accepted with probability 0 or not. It may be both, right? It may be the case that yes or no. But if your automaton is limit deterministic, then a run, an accepting run, cannot go through infinitely many of these things, because an accepting run must jump at some point. And from that point onwards, there is never a choice. So this means that every accepting run has probability bigger than 0. And therefore, the question whether the word is accepted with probability bigger than 0 can be reduced to the problem whether the word is accepted. Okay? And that makes a big difference, right? That helps. So that's the reason why limit deterministic automata are useful for probabilistic model checking. Well, and now if you want to construct limit deterministic Bushy automata for LTL using this, what do you do? Well, how do you construct your automaton A phi? Then you have an initial component which you are just tracking this formula, and that has this size, right? Or you could do it non-deterministically as well, it doesn't really matter. And then you jump. And when you jump, you are guessing everything. The jump corresponds to guessing everything, and then you just jump to the correct formula. Okay, so if you just jump to the correct formula. And this DBA is going to be the intersection, of 3 DBAs, and it's blah, 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 right? Here you can take them deterministically, and then you get the final bound. Okay, so it's actually exactly the same thing. So a couple of remarks, and we are done, right? Well, my claim is that I could, once you understand the Master Theorem, this took about 15 minutes, right? And if you want to do it, if I would have had to explain you the equivalent results, but using the techniques that are known, then it would have taken much longer. Good. So a couple of remarks. The Safra's translation, which could be the translation from MEA to DRA. As I told you, the main difference for me is that it is a monolithic construction, right? You don't see the structure. And what are the potential advantages of, at least potential, and we will see some of them real, of a structure construction? Well, imagine, for example, that you only want to execute the DRA, right? You don't have to explicitly construct it. You can just keep it as a you can keep the structure description, right? And execute the things synchronously, all the components synchronously. So for instance, that could be interesting for runtime verification. Also, what you have is a large combination of essentially tiny little automata. Most of them are very small, right? Even though the theoretical limit is double exponential, in practice what happens is that these automata that you have to combine, they are all very small. So then you can, anything that you can do to show that one of those automata has empty language, and since they are small, that's not too expensive, you can do before constructing the intersection or the union, right? You can get rid of components. And also the states, they are always formulas. And then, for instance, if you have two different states, our bounds, that this is at most double exponential, were obtained by saying, well, there are at most 2 to the n propositionally equivalent and non-equivalent formulas, right? So we were saying, if you only use propositional equivalence in order to see whether you can, in order to not to construct more states than needed, right, then you get this bound. But you can use anything on top of that. You can use any kind of reasoning to say that two formulas are equivalent. Okay, you can add a little bit of temporal reasoning, for instance, equivalences, and then if you show that two states, the formulas labeling two states are equivalent, then you can just merge the states. Okay, and then you can get reductions. So this allows you to use any kind of reasoning there. So logical reasoning in order to reduce the automata. That's something that the Safra construction does not allow you to do, just because you forget about the formula, essentially, right? Okay, yeah.
So for probabilistic model checking, in some sense, it doesn't cost you for going from DRA to DGRA.
Yeah, no, in fact, what you can here directly construct the generalized driving automaton, and then you don't have to degeneralize.
Right.
Yeah.
But if there it's all about the analysis of n components.
Yeah.
And it's easy to check whether the Rabin condition hold or generalized Rabin condition hold. But for synthesis, you need to solve the game. And
That might be. We haven't looked at that so far.
we have algorithms for parity games.
Yes.
For Rabin games.
For generalized Rabin games, I don't know.
Nothing jumps to my mind about generalized Rabin game, how to solve the game without degeneralizing
Yes.
the condition, and what is the complexity of degeneralizing the condition?
Well, it will not. I don't remember exactly, but definitely it doesn't take you to triple exponential. That's not the case. And whether it is 2 to the 2 to the O of n or 2 to the 2 to the O of n square, I could not tell. Can you tell?
I could add something there. So of course you could use the normal degeneration algorithm to degeneralize, but since we have the structure, we can add directly into the construction. So it makes the construction a bit more complicated, but you don't need to do the standard approach.
This is actually already implemented.
That's
Right, we
right.
have the implementation there, yeah. But then you have the size, the maximal size of the degeneralized condition is also 2 to the 2 to the O of n, or
No, what you get is a sum. So what you do instead of like the degeneration, you have this counter where you run all the automata in parallel and say you're next, you're next, you're next, you're next. You now can, because we have GF, what we have to check, you can say, okay, we just check this formula and the other ones are just not taken care of. And then you later can CA, because you have CF. So you can delay as long as you want to. And this makes it cheaper than the standard construction.
right. So, and then the idea is that all this has been implemented in the tool, the Robinizer tool, which started as a tool for deterministic Rabin automata, and which has now been expanded. And Jan Skretinsky initiated the project around 2012, and in the meantime, the actual version is Robinizer 4, and you can find it there. And Robinizer is now using the Omega Word and Automata library, so which is a sort of part of Robinizer and at the same time a spin-off of Robinizer, and this is what Salomon has developed, started around last year. And again, you have a web page here, and now it is that Salomon can give you a short demo. Sure. Take this. Thanks.
So let's move this now from theory to practice. And yeah, okay. This is so since I'm showing you sometimes terminal output and websites, you just have to shout if it's too small, and I try to increase it. I try to check it beforehand, but it might be too small. So as Javier already told, there is all now, and this is the standard library we developed at our chair to work with Omega Automata and Omega words, and basically the need for that was that whenever we have a new idea for construction, if you start from scratch every time, it takes quite a while to get done, and now implementing a new translation is just a matter of defining a new successor function, and we are done with it. So part of this library is lots of different translations from LTL, from NBAs to LDBAs to parity automata, and also to these new special ones we call an Emerson layer automata, which are basically Muller automata with a symbolic acceptance condition attached. And most of these other translations are also part of Rabinizer. As input formats, we support, of course, LTL, but also the temporal logic specification format. So we can take input from the synthesis competition and also translate it to LTL and automata. And of course, at output and input, the standard Hanai Omega automaton format. And of course, you find standard automata algorithms like an SSC decomposition and so on. So if you want to build a tool in Java that does something with Omega words and Omega automata, this is basically the choice you can have. And if you don't like Java because you write a nice tool in C++, we also have a C++ interface for you. And just to show you the website, hopefully this works now. Here is the official project website. Of course, this release is a bit older. It's from spring this year, but we are working on providing something new. And let me also show the website of Rabinizer 4. This is also at the moment in the process of being published, so don't expect too much now and too complete information, but you can find it here. And while I'm already showing websites, this is, okay, that's of course too small. This is the instance. The link is also on the slides where you can access the code, see the issues, and collaborate if you want to. So let's back to the slides. So as I told you, Rabinizer was this, and Javier already told you, this project that started out with constructing deterministic Rabin automata, but then started to add more features like translation to parity automata or to different kinds of logic. So there's this frequency LTL, which is rather close related to LTL, and you can apply the Rabinizer construction to also this extended logic. So let's see a demo. Here on this website, so you can also open up on your mobile or computer. We have an online installation.
Not on your computer.
Not, yeah, later, after the lecture. So you have the following syntax. You can use lowercase letters for your atomic propositions. All the uppercase letters are temporal operators. Then you have the standard encoding for not negation as the exclamation mark. You have the ampersand for the conjunction, the bar for disjunction, the XOR implication, and so on. And you don't have to put in negation normal form. We do that for you. So let's open up the example website. So let's start with something simple. Is that rather readable? I can't tell. Okay. So the simple formula is here, this FUM formula. And let's see what we can do. So down here we have a selection of the different translations. As you can see, over the years we developed lots of ones. These are the original ones. So this is the Rabinizer with degeneralization that takes you from the deterministic generalized Rabin automata to the normal Rabin automata. Then you have a translation to parity automata using that original translation, using index appearance records. And then you have two new versions for DPA translation that use this LDBA construction you have seen before in a clever manner to avoid this going through index appearance records. And there are two LDBA constructions. You're wondering why are there two? You've just seen one. There has been another one before that just focused on the G's, and the new one you've seen focuses on G's and F's. So basically the formulas that are almost everywhere true and the formulas that are infinitely often true. So this means this guessing F. Then we have a couple of options down here. So the first one is show state annotations. So Javier already told you that all the states have an LTL formula. You can label them. And of course, you can use the translation and say, please also show me this label. This will give you big pictures, but it will tell you what the states have, or what the semantics of the state is. And the second thing is you can say you want to have a simple state space construction that is very closely related to what Javier told you. But of course, we implemented additional optimizations on top as this extended equivalence checking on LTL formulas. And then the LTL formulas are pre-processed and look very horrible, and you don't want to look at it. But for sake of presentation, you can just say, let's keep it simple. And this option here, state-based acceptance. So everything Javier told you was phrased in the terms of accepting states and accepting or rejecting states. What you nowadays do is not really focus on accepting states, but in all implemented tools you have transition acceptance. And the reason for that is that transition acceptance is just more succinct. So a small, easy example would be the following automata, where you say you want to see infinitely often A. Then you have always in state-based acceptance to have two states and circle between them. And if you use transition-based acceptance, you can just have two transitions here, and one of these are accepting, namely the A transition. So let's see what happens if we construct that. For that simple formula, you get, so this is from From fragment, so we just apply the after function. And what we get here is that state. If you read an A, we go down here and wait for the B. And if we see the B, we can accept and go to true. Or else, if we see an A and not a B, we stay here. And if not, we have to move back to the initial state. And as you can see, the red box tells you that that SCC doesn't have an accepting cycle in it. And the green box tells you, OK, here, something is accepted. Let's move on to the GBR fragment, GW fragment. So we have a new formula up here. That's A weak until B and XC. And what we get here is the dual to the thing we've seen before. But notice there is no false state. And the reason is because we dropped the false state. That in this definition, deterministic means at most one transition. It's not complete. But of course, you can always add the false state to make it complete again. But then you get more edges and it's more complicated. So, moving on. So. If we look now at GFA, so that would be from the GFUM fragment, the translation uses exactly the LUA translation you've seen from Javier before, does the following. It keeps initial component unfolding GFA, and at some point decides, okay, now is the right point to move on, and then guesses that A is holding infinitely often, and we prefix this here with an F. And of course, as you've seen for GFUM, we would have a direct construction, but we do not detect this in this case. In the simple case, we do not do this, but if we now activate the more enhanced translation, and wait a second, goes back to Germany, and comes we get a simple automaton with just one single state, checking this. So, but feel free to ask questions. I can change the settings and then you see the results. So, let's move on to a more interesting example. So, that would be G, A, or FB. So, there we actually have to guess something. There has to be a decision. Does B hold infinitely often or doesn't? So again here, in the automaton, we have the initial state. We circle around and wait and guess the right point. And then we can either decide, yes, the B is going to hold infinitely often. And then we start substituting or evaluating the formula. And then, of course, G, A, or FB becomes trivially to true. And we can move on. And the only thing we have to check here is FB. On the other hand, if we guess that FB now doesn't hold anymore, we can simplify again, and now we have to check GA. So all nice, all simple, all small. The last example I have here is something a bit more complicated here. So it's an FG, and you have an XOR in the middle, and then you have another G and an until. And if you look here at the automaton, it's getting really huge. It's like Looks like a map of an old town or something. So
Can you make it smaller?
yes, let's make it smaller. First, drop the.
Okay.
Oh, you mean zoom out?
Yeah.
Yeah,
You
I
also
can.
make it
Yeah,
smaller.
that's zoomed out. But let's make it smaller. So first of all, we're dropping the state annotations and we're using a more clever construction. And then this is what we get. It's a bit smaller, more understandable. And as you can see here, these are the accepting components. So here we did the guesses, and this is the initial component where we wait until it's stabilized. Any questions so far? No. Then back to the presentation. So now I just shown you some examples and looked nice, but the question is, how does it compare to existing translations? And I brought two comparisons from a Tucker's talk this year. So this is a slightly different construction because we don't have evaluated new construction. I have to show you old data. But what do we compare here? So on this axis, this is our translation. It gives you from an LTL formula a DPA using this logical decomposition. And on this axis you have Spot. And Spot is the leading LTL to automata translator there is. And I think this year at the synthesis competition they made, but Bernd, please correct me, they made second place in the LTL synthesis track using...
They produce deterministic, this is not deterministic automata?
They're producing now deterministic automata also.
Which one? Also DPA?
DPAs, yes. And this was used this year in the synthesis competition to get to second place using explicit parity game-based synthesis approach. Yes. So what you see here is the first set of formulas is a standard set of parametrized formulas collected at an LPAR 13 paper from other authors. And this picture basically tells you we are as good as the other, and most of the time we are better. So the green part is basically where we excel the other tool. Going on, so now the question is what happens if we look at synthesis and random formulas? And there the picture is not so clear. So for random formulas, you have a slight tendency to in our favor, but there are still some formulas where we do not perform so well. And for the real benchmarks from the synthesis competition, you have also slight tendencies on our side. You have some outliers where we are able to produce automata that are rather succinctly, but there are still cases where we do not excel Spot. Yes? Oh, the benchmark set is called Akacha. So this is from the synthesis competition, the benchmark set from Akacha. Yes?
When you refer to a real-world formula, how complex does the property described by
The parity color. I don't have any answer for that at the moment.
Suppose we take a human being designer to
Mhm.
design a machine for that automata. How does this human design machine compare to your synthesis result?
We're not doing synthesis at the moment. It's just the automaton you obtain.
Yeah,
Then
so like writing some code, develop and design this finite state machine, and we can synthesize it to hardware.
no, so in the first step you get the parity automaton, and then you split it to an arena, then you play the game on the arena, and then you synthesize the controller from the winning strategy. So we're just in the beginning of this process. So of course the size of the parity automaton gives you some indicator, or it might be an indicator how good the controller is at the end. But it might be that the winning strategy is very simple, even on a big automaton, and then also your controller becomes very simple. Good. So then after seeing translations, let's move on to probabilistic model checking. And I brought a small example from a paper we had last year, I think. So what we're trying to check is the randomized mutex protocol. This was described in 82. And you don't have to understand what this does. It basically tells you, okay, down here you have a critical section. And before here you have some state transitions that somehow try to figure out who is able to move to the critical section. And if you look at Prism, they take this description of a process and then translate it to an MDP and then do the checking the checking. And in this case, we want to ask, okay, what is the probability for like the best probability for the best scheduler, such that in the critical section as most one process. Okay, that's our safety property. And here we have the non-starvation, so everyone can access it again and again. Yes, please. So, sorry, can you please speak up a bit? That's Pnuli. So,
Repeat the question.
okay, the question was, what is the article I'm referring here to? To be honest, I don't know the title now by heart. I would have to look up in our paper. So that's the paper reference we use. It's Pnuli Zuk 1982. Probably the title is very close to randomized features protocol. But I have to admit I don't know the exact title now. So let's move to the example here. So, no, this is small, but don't worry, that's the protocol we've seen before. Down here we instantiated 4 copies, or 3 other copies, and then we define here the properties. For example, let me look here, is the number of critical processes. The number of processes in the critical section. And then if we look here at the properties, for example, that one is exactly the property I've shown you before. And of course you don't see our automata construction now, but in behind there it is running. So we can now ask, okay, please verify this. Okay, this is also a bit small, but I don't know if you can read it, but here is, okay, the probability. So there is a scheduler such that the probability that this property holds is 1. So let's go back to the model and maybe break it. So what about a nasty process just stays in the critical section? So I changed here the line from moving onto location 11 and just say, okay, I'm staying in 10, never giving up the critical section anymore. And then we go over here to the properties and verify again. It tells you, oh, there is the probability 0. So there is, the best you can do is nothing. And that the reason is basically one process blocks and then all the others starve and cannot enter the critical section. Questions for that? Yes, please.
Speak up.
Yes, yes, of course. It was just for sake of presentation. So for Prism, there's a command line interface. For our tools, a command line interface. And most of the features are only available via the command line interface anyways. So, back to the presentation. So the last part, synthesis. And now we're using here this synthesis chain where we switched out the NBAs before we go to the DPAs with the LDBAs. And I guess you already sick and tired of that formula. So that was our simple arbiter telling us whenever there is an input, you get an output. So, okay, we assume that this is realizable. What about changing it a bit and saying we now have we give the first process, or like the first client, a special priority. So we guarantee him that we immediately satisfy his request in the next step. So I want to make a quick show of hands. Do you think the specification is realizable? And if you don't know, just follow your guts. So, realizable, hands up. Unrealizable? Okay, then I have to ask unrealizable guys, because no one said it's realizable. What do you think that's why it's unrealizable? Yes, basically the first process can spam the controller and ask, give me, give me, give me, and then the second one starves. So one solution would be to assume that at some point the first process stops asking for the resource, or maybe adding some room here to breathe and say, okay, we have a small window of 2 steps to answer the request. So let's see, how would you come to the same conclusion? So is that readable from the back? Okay. So let me look up. What was the first specification? It was that one. So that one is realizable, as you guessed and note. And then if we look at the one where we have just the one simple X, let me change that here. it tells us, okay, this is unrealizable. At the moment, it doesn't give you any reason why it is. We internally have it. There is a strategy generated, but at the moment, we just output realizable, unrealizable. And then the last one with the room, this is realizable. So far so good. And this concludes the small presentation and demo. So please try it on online. You can get the official stable code here. I put some additional winter school material on that website, so if you follow that link. You can also get here a draft of our approach. Like, this is a very technical description. Again, it's for that you can re-prepare and look what we do, but please do not distribute. And here you find somewhere at the back, let me just show you, here the Master Theorem with proof and everything attached. Yeah, two couple other words. So if you're interested in that translation, but you need it in a very rigorously mannered, verified version, we also can provide this. There is an Isabel version of the whole Rabbinizer with code execution included. And if you're interested in other projects, just check out our GitLab site, and then you can see what else we're doing in our chair. Thank you. And then I guess I hand over to Javier now.
I need 2 minutes.
Oh, sorry. Get that out here.
So you are the first persons that we explain this new construction to. So thank you for being our guinea pigs, right? We just wanted to see how it works. It's not, of course, totally appropriate for a winter school, in the sense that, well, you usually present some things that you have trained a little bit more. But, you know, we love to communicate our research. I particularly think that communicating what you are doing is an exciting part of the process. And because of that, I want to tell you a joke. It's a joke that I heard from a German kabarettist, so it's just a stand-up comedian, Bruno Jonas, quite famous. And he had a very beautiful program about Christian religion. So he was telling very good jokes about the Pope and the Virgin Mary and so on. But then he concluded it by saying, but actually, the real masters of religious jokes are the Jewish. And I will tell you a joke, a Jewish joke, right? And the joke goes like this. So the Grand Rabbi of Jerusalem, and this is the Grand Rabbi he used, so actually it fits, right? The Grand Rabbi of Jerusalem is crazy about golf. He loves to play golf. And he's now on a golf holiday in Scotland. And unfortunately, during all week, the weather has been dreadful. It's been raining cats and dogs, and he hasn't been able to play. And now he wakes up, and then he sees the sun is shining over the highlands of Scotland. The grass is wonderfully green, and the lake is blue, and there is a light breeze that makes the golf course even more interesting. There is only a little problem. It is the Shabbath, right? But he's looking through the window. So enticing, right? So wonderful. He can't resist the temptation. He picks his golf clubs, and he goes to the golf course. And, you know, God and Gabriel are watching from above. And Gabriel says to God, you are going to punish him, right? How are you going to do it? Greek style with a lightning, right, that's going to fry him? Or is the ground going to open below his feet and he's going to sink? And then God says, wait and learn, right? And then the Grand Rabbi of Jerusalem goes to the tee, puts the ball in the tee, takes the club, makes the swing, pack, you know, and the ball flies. Hole in one. And Gabriel says, what are you doing? This is what you call a punishment? And then God says, you don't get anything, right? Who can he tell it to? So thank you for being the ones we could tell it to.